Welcome to the closing ceremony of the Mendeleев 2021 conference. We kindly ask all the participants to take their places as we are ready to start.
Your hosts for today are Georgy Misikov
And Taisia Maltseva.
We are glad to begin our closing day of the ceremony with the lecture of our foreign guest. Please meet the full professor and head of the Department of Physical Chemistry, University of Vienna in Austria, Professor Peter Lieberte. Professor Peter Lieberte is a co-author of more than 140 papers indexed in Web of Science and a participant of roughly 180 conferences, the chairman of the International Scientific Committee of the International Meeting on Chemical Sensors Conference since 2018.
He received the Wolfgang Goepel Award in the International Symposium of Olfaction and Electronic Nose in 2007 in St. Petersburg and Fritz Feigl Award from the Austrian Society for Analytical Chemistry in 2011. He is currently a member of the Editorial Advisory Board of Analytical and Bioanalytical Chemistry and a member of the Editorial Board of Sensors and Actuators. Professor, thank you very much for being with us the whole week. Now, please take the stage.
Thank you very much for the kind introduction. Though I have to admit, and for the warm welcome, I have to admit I haven't been here the whole week for two very simple reasons. On Monday was the first day of school of my son, which I stayed in Austria. And the other reason is that due to the current situation, Austrian Airlines do not operate their direct flight to St. Petersburg, which means I had to come in through Sheremetyevo, which takes about 3 times longer than the direct flight. But I have very much enjoyed the time being here, and I thank the organizers also very much for having me here.
It's a great pleasure returning to, not exactly this hall, but to St. Petersburg for a conference after the ISON, and seeing still so many people on the last day. So what I want to talk about today is, as you see from the title, Molecularly Imprinted Polymers in Rapid Analysis, Challenges and Chances. So this is now a test if you have really read the program book, because there it's the other way around, chances and challenges. And as it's a conference for young scientists also, I permit myself to put in a few things where the questions are really open yet. In other words, which have not worked. Because usually if you go to a conference, you see all the glitzy things, but from your everyday experience in the lab, you might ask, how the heck are they doing this? So just very briefly, what is the logic behind it? I think I tell you no secret if we say that focus of chemistry has switched or developed very strongly in the last 40 years, because let's say until the 1970s, we were interested in how we can make one molecule from another, how things interrelate, and then in the 1970s, 80s with Jean-Marie Lehn, we got into the question that basically interests everybody who sits at the hairdressers and sees all the journals devoid of any information. Basically, who does what with whom? And you know, in chemistry, it's always a little bit more technical terms, so it's supramolecular chemistry. What do molecules with each other? So basically, the development from a single molecule to assemblies of molecules. As you know, also interactions with antibodies and antigenes, or also here binding between DNA, single strands based on hydrogen bonds, which is not the classical chemistry in a way. That said, in my group we use 3 different synthesis strategies, and I skip through the animations a little bit, for actually generating selectivity, for getting sensors, biomimetic sensors that take concepts from nature, such as antibody-antigen interactions, and implement them into artificial materials, because chemistry still of course, takes concepts from nature and tries to make them, well, let's say better or technologically feasible. So we had a little bit on affinity materials. We don't do too much on that. We do self-assembled monolayers, which I will skip in today's presentation. We took up a little bit more in the recent years again. But our workhorse are molecularly imprinted polymers. I don't know if you're familiar with the concept of MIP. Basically, the idea behind it is so simple that it is surprising it works. And as a matter of fact, it was a Russian scientist, Polyakov, who first observed it in the late 1920s when he realized that if you synthesize silicas in the presence of organic solvents, they show affinity to the solvent, but not to other solvents. But probably it was a bad time and people were not interested so much in that time. So basically the concept was taken up in the 1970s and 1980s and since then has kick-started. So basically the idea is saying we take a molecule as a template and synthesize a highly cross-linked polymer around it that shows interaction sites and cavities that both in terms of steric and chemical properties match our target molecule and thus rebind them. That's the theory. So it's basically as kids, you know, casting traces of animals in the woods or something like this on a molecular level. Before we go into that, I need to walk you a little bit through the quartz crystal microbalance, which is our workhorse in terms of using them as sensors. Quartz crystal microbalance is a mass-sensitive sensor. What you see here is one of these examples, and you will see a few more photos of those. Basically, it's a thin quartz plate, you see it here from the side, onto which we deposit electrode structures. And the interesting thing is these are two electrode pairs, so the counter electrode is on the back side. Quartz being a piezoelectric material, so if you apply voltage on this, it changes its geometry. In the concrete case, the two faces shift against each other in a shear motion, which also means that if you apply alternating voltage on it, at a certain resonance frequency, you will have, or you will transform the electrical energy into mechanical. Then you're in oscillation. Sounds very theoretical, but if you're old-fashioned as I am, these are operated by those. Okay? And the interesting thing is that the resonant frequency, of course, depends on the thickness of the quartz. So basically, half a wavelength has to fit between the electrodes. But it also depends on the mass on the electrodes. So if you deposit mass on it, frequency will decrease. So we'll see quite a few curves like this one, where we have a certain equilibrium frequency. We expose our quartz to the analyte. Frequency usually decreases, not always, but usually. And if you take back the analyte and flush again with solvent or background gas, we get back to the initial value. So I want to go in with measuring curves of ferritin with surface molecularly imprinted polymers. Don't let yourself be confused. The only difference is we have a comparably large protein here, so we don't grow the polymer around it, but we put the ferritin on a stamp and just squash it into our oligomer solution on the quartz. And on the first side, it looks very good. It's a molecularly imprinted polymer channel here in red, and the non-imprinted polymer, which we always run as a control on the second electrode, in green. And as you see, depending on ferritin concentration, we have these frequency responses, and things look very good. So let's call the journal and tell them we sent them something. No, don't call journals, they don't answer. It looks very good, and it looked very good to us until we started looking into the details, and that's what I said. If you have a negative result, it's very natural to think about it, why it went wrong. If you have a positive one, maybe you want to think and retry if there may be something wrong. What actually happened here is that we found out that if we use only the matrix, we get basically the same effects than with the protein, which is bad news.
And then we thought, okay, what could be the problem? So we go little bit away from chemistry into measuring science. And then we saw if we change the geometry of the quartz, we get completely different signals. So basically from very huge signals down to almost no signals at all. And the only thing we changed was that whereas in this case we have metallized distinct electrode patterns on the front and on the back side, we had these comparably large effects, and when we fully metallized one of the faces, one of the sides of the quartz with gold, and more precisely the one that faces the liquid, the sample, we get much lower effects. And looking into electronics literature a little bit, and that's tricky for a chemist, we found out that it's not only mass, it's not only viscosity, it's also charge. And of course, with the background, you change charge because you change liquid conductivity and so on and so on and so on. We retried those with tobacco mosaic virus, for which there are actually publications which were difficult to reproduce, even our own ones from the group 15 years ago. So not my concrete, but from the group. So we tried different polymers and didn't see very pronounced effects here. And what we did then is that we made AFM images of our imprints after the QCM measurements and saying, okay, after the measurements, we hardly didn't see any viruses on the surface. Here we have something in citrate buffer at 10 millimolar, pH 5.4. We see a few tobacco mosaic viruses. These are these light spots here. But otherwise, we just see our very beautiful cavities. So you could publish any of these images in a MIP paper and it would be accepted. That's not an issue. But we don't see binding. So what we learned from this is that obviously the thin film interface of such an imprint is much more complicated than hundreds of papers published every year try to make you think. Whereas on a different polymer, if you look, we had very good binding on both, and if we looked into the AFM, we actually had binding both on the imprinted and on the non-imprinted side. So the polymer affinity in this case was too good. So the question was, and for the TMV, I don't have the answer because we really need to look into the physicochemical details of molecularly imprinted thin films for these types of analytes. We have others where it works better. And we are just beginning with that. So we need some really good physical chemistry. We need some modeling there. But the question really for us then is, how do we achieve optimal affinity? We're again with the who with whom and so on. Yeah? Because, well, if you keep this interaction non-selective, you get into trouble, to put it that way. And one answer is actually solid phase synthesis. It is an answer found by the group of Sergei Piletsky, who is at Leicester University now, and also by Carsten Haupt, who is a very good polymer chemist in Compiègne. And they tackled the thing by saying, okay, we immobilize our analyte on a surface, in this case a silica gel or glass beads, and then we grow the polymer around it. And once we have the molecularly imprinted polymer, we do two washing steps. One washing step at low temperature, which removes all the non-imprinted and the low affinity particles. And then a washing step at high temperature, low meaning 20, high meaning 60, roughly degrees centigrade, where we remove the high affinity particles and collect this. And with this, they overcome two major problems of molecular imprinting, one of which is binding or very high distribution of binding affinities. And the other one, the fact that if you synthesize it that way, you usually have one binding site per particle and not several. So it's a very smart idea. Unfortunately, not ours. However, and that brings us back to the thin films. In the thin films, we cannot do that. And what those papers usually don't tell. These particles, as I will show you in our own work, bind quite well but in terms of monomer input, you have a yield between 2 and 3%. So that's the downside, and everybody who works in organic synthesis will know that for a one-step process, 2 to 3% is not exactly what you aim for. So we tried two different things, and I will show you one with silica molecularly imprinted particles, which we did in an Ostwald ripening process. So the original work is on organic polymers, but we also tried with core shell polymers, where we first prepared an organic polymer and then grew through Ostwald ripening silica nanoparticles around that. In this case for human serum albumin, because it's a proof of concept. And you see synthesis works quite well. So what you see here, CS are the core shell particles, Si are the silica nanoparticles, and this is synthesis time, 3 hours or 5 hours. And you basically see that the core shell particles surprisingly are even a little bit smaller in diameter than the pure silica particles, so we wouldn't need to look into synthesis here, but we are more interested in the analytical side of things. And you see that the size correlates quite well with synthesis time, which is not so surprising, but which is interesting for us because the larger a particle, the more mass it has. And the more mass one single particle has, the higher the signal we expect on the quartz crystal microbalance. So that's the idea why we would use also a material like silica. So we tried through fluorescence quenching, we tried to find out if there are binding affinities of the system. So what we did is, here you see one example, we exposed this silica MIP to, or in this case, to human serum albumin in solution. And what you see is with increasing HSA concentration, you go here from red to blue, and we get decreasing fluorescence through to static quenching of the system. You can plot so-called Stern-Volmer plots against the concentration of nanoparticles in ppm, which basically gives the initial fluorescence intensity divided by the current one. So usually in these Stern-Volmer plots, if you have quenching, the values increase from 1. And basically, okay, this is a little bit less sensitive than the one I use in my lectures. Basically, the higher the slope here, the better the binding constant. And you see that basically the binding of the two core shell particles is similar. The silica particles, especially the one for 5 hours, which surprised us a little bit, is lower, but we still need to look into the effect whether this has something to do with the fact that we have just fewer binding sites than in the solution, because these are mass concentrations, not particle concentrations. Those are quite tricky to calculate because of the size distribution here. And then we said, okay, we verify those in our QCM assays, and what you see here is one of our measuring cells. So we will connect the electronics here. Fully metallized QCM surface, that's very important in this case, because what we do is that we immobilize our analyte on the surface and then basically expose it to our molecularly imprinted polymer, which reverses the logic of molecularly imprinted sensors. But it makes sense from an analytical point of view, because actually, as I told you before, a single particle is much heavier than a single protein molecule in this case. And it makes sense to say, okay, the compound that gives me my signal is heavy. We just need to be careful, and I left the optimization out here, we need to be careful to put spaces in between the self-assembled monolayers, because we know that if the protein molecules are too densely deposited on the surface, the particles don't bind for sterical reasons. So they need to be, the molecules need to be something like a few tens of nanometers away from each other. But that's fairly easy to do. What we usually do is having one with the target analyte, which is human serum albumin, and the other one with the competing analyte, lysozyme. It is the easiest way to do to make sure that the surfaces are somewhat similar, because standardization is a bit of a problem here. And if you look at this, in this case for silica, the non-imprinted polymers don't show any affinity to that surface, or very low one, whereas the MIP particles that we synthesized for 5 hours On the human serum, albumin give these very beautiful negative frequency shifts, which are concentration dependent. And they don't do that on the lysozyme, or to a much lesser extent. So we can learn two things from here. Imprinting works, so the synthesis process works, because otherwise we wouldn't have the difference between the two. And we do have selectivity, and that's what we wanted to achieve. And the beautiful thing is that these particles, and that's what we know from the Sternformer plots, these particles basically on average have 1 to 1.2 binding sites per particle. And from the analytical point of view, that makes it interesting, because that means we can use them in competitive assays. Basically really targeting at replacing antibodies, natural antibodies, because if you've ever worked with those, you know those are pretty expensive and require a certain way of handling them. So if we look at this, what you see for the different type of particles, the general message is that the non-imprinted particles show comparably low affinities and rather constant over the concentration range, with the exception of the silica nanoparticles that we polymerized for 5 hours, which also happen to have the highest affinities in the molecularly imprinted particles, which is not a problem, because what we are interested in is the difference between the two, and that's still the largest for those ones. So the PhD thesis is still ongoing, but at the moment we are working actually on competitive assays with this silica-based material. So this has worked. If you remember, the starting point was, how do we optimize polymers? So this approach definitely works. With this, I want to switch a little bit. So this was a glance of analysis in terms of using that material for analysis. But what I also told you is, despite the fact that we have molecularly imprinted polymer literature for 30 years now, it's today dominated by China, like very much in science. And basically, you have thousands of papers per year. And I claim that we still don't fully understand the physical chemistry at the interface, for a range of reasons. And what we want to do is to understand that better in the next years. And I want to show you a few steps we undertook in the last 2 years. And for that, we used bacteria, simple E. coli, for imprinting, because they have a nice size. So we can see the imprints in the microscope. And basically, they are large enough that we can do a few experiments. You see it here, Raman spectroscopy, where basically space resolution is in the just sub-micrometer range and not nanometer. We are just implementing TERS. So maybe if you ever invite me to another Mendeleев conference in 5 to 10 years, I can probably show you better resolution here. But don't take it as a promise, and don't take it as a hint to invite me again, though I love being in Petersburg. So here you see the surface imprinting process. We have seen this already. And here you see one of these polymer surfaces where we basically left the prints of the particle behind. What we used was AFM. You will see quite a bit of atomic force microscopy images. But what we are also using here is confocal Raman microscopy, because that allows us to study the interface. Although, as you will see, it is a little bit tricky. That looks on the first side, and there is a reason why I look at you, Dimitri. You will see why, and why I'm looking at you. So the idea is that we said we went for polystyrene, gives very beautiful cavities. And we wanted to, in the first step, we want to distinguish between the polymer and the bacterium. So what you see here is a single Raman spectrum of such a molecularly imprinted polymer, in this case at a place where we don't have any bacterium in there. And we could walk through this Raman spectrum if I would have assigned all the bands, but it's not of importance for our further discussion at the moment. In the AFM, we could prove that these are cavities. Why is this important? Because if you look here at the light microscopy image, you cannot distinguish between cavities that are occupied and that are non-occupied. So you can tell that you have the structure, but you cannot tell if there is a bacterium in there or not. But AFM tells us, okay, it's holes, it's not bacteria. And then we said, okay, is it possible to use Raman imaging to distinguish between the polymer surface and the imprints? So basically what we did is we looked into this section and focused here only on this spectral region of the Raman spectrum, which is basically, as you know, in the area of the aliphatic CH bands, and see if we can see a difference. And the Raman software, what it does basically, it runs chemometry over the data and then translates this into an image. So this is called Raman TV for that supplier who sold us our Raman machine. Others will have other names. And what you see here is actually a Raman TV image, not AFM, which means band intensity is comparably high here and comparably low here. And that means that we really can depict the imprints in Raman. This sounds spectacular, so I could stand here and ask for your applause. As a matter of fact, it is a bit less spectacular when you know that basically one voxel, which is in focus on the Raman, is about 800 by 800 by 800 nanometers, and we don't change the focus distance when we scan, which makes it more logical. But still, it's beautiful to see that we can distinguish. Next step is, can we distinguish between the polymer and the particles? And that becomes more tricky because on first sight, the Raman spectra of the pure polymer and of the Raman spectra containing the bacteria look very, very similar. And that's where chemometry comes in. And indeed, it turned out possible. So what you see here again is a Raman TV image, not AFM. It's, in this case, vibrational spectroscopy information, where we see here the parts that are occupied by bacteria. We see in the midtones, we see the polymer, and in the darks, we see the imprints again. So we can actually visualize that thing. And I'm not aware that anybody had done this before on such systems. And if we compare it with AFM, again here light microscopy, you have here the AFM image and here the Raman TV image, and you see that the two correlate very well with each other, which basically is a way of analytically validating one data with the other. Because the system is built in a way that, let's say at least in the micrometer range, you can make sure that your AFM tip is in the same region as your Raman excitation. It's not absolutely exactly. It's we had long discussions with the company about that, but on this size range it works. Okay, next step. Next step is differentiating different bacteria on the surfaces. And that gets things more tricky because if we are very blunt, what is a bacterium? Water, fatty acid, proteins, nucleic acids. That's it. It's very coarse grained, but you get the picture. So Raman spectra of different bacteria, again, if you look at them with the human eye, look very, very similar. But with chemometry, if you pick out basically, or if you amplify the differences, that's what basically, well, discriminant analysis does a lot. So it cuts out the similarities and blows up the differences between. It helps, of course, differentiating. So we tried this with E. coli and Bacillus cereus, again, on polymer surfaces. You have here the mean Raman spectrum of an E. coli and the mean Raman spectrum of B. cereus. And now I could say it's like for in these kids' pamphlets where you have two images and they have to tick the 10 differences. Feel free. Okay? It may be a bit tricky. Meaning that basically, and it's not surprising, you have this aliphatic, you have quite a lot of signals in the aliphatic CH range, you have quite a lot in the fingerprint range, and that's it at the end of the day. Nonetheless, if you fill that into a partial least squares discriminant analysis model, which we didn't develop, so that comes with the software, that's our weak point, we don't develop chemometry, we use it, then we can actually establish a model that from parts of the spectral bands, very much in the CH region actually, can discriminate between the two bacteria types. And actually, out of 20 spots we tried, we have a correct allocation of 19, which on this admittedly small data set means prediction quality is about 95%, which is quite good, I think, given the fact that we are on a polymer, so we have to subtract the polymer background, and given the similarity of the different bacteria spectra. We can even go further and distinguish them in the imprints. So again, one of these nice images where some bacteria are in there. This is now the pure Raman TV image, but if you take that one step further and run the discriminant analysis model again through that, you get for each pixel a class prediction for polymer, for Lactobacillus lactis, and for imprint. So actually, the model again works, well, there is room for improvement here, but I'm always surprised to see how close these images match each other, given the very small differences. So basically, we amplify a lot of noise here too. So as said, it's work in progress. So these images are maybe 1 year old or something like this. So there is still a way to go, and one direction where we want to go, I want to show you on another thing, is I want to show you how fine you can get down with AFM in imprinted polymers and in these matrices, and then get back to spectroscopy at the very end of my talk. We tried a different synthesis here for a different application. What you see here is not astronomy, it's actually SEM, although it very much looks like astronomy. But what we did here was synthesizing bacteria imprints with so-called Pickering emulsion polymerization. So all of you know emulsions. And the difference between a usual emulsion and the Pickering emulsion is that in a Pickering emulsion you don't have a surfactant, but you stabilize the interface with microparticles. So it is known that if you have a biphasic system, some microparticles go into the interface between the two liquids and stabilize it. And actually E. coli stabilizes oil in water emulsions. And also water in oil, but then you would have these hexagonal systems, bicontinuous systems. And as a matter of fact, what we tried is seeing if they really leave behind imprints in those polystyrene particles, and they do, as you see here. So it looks a little bit like a planet's surface, but it is not. We can get a step further. If you look at an E. coli in AFM tapping mode and try really hard in optimizing the parameters, what you see here are structures like this. So this is the error image, this is the phase image. And in the first step, you might say, well, that's some kind of noise, but as a matter of fact, it's not. It's known from microbiology that if you expose E. coli to very hydrophobic surfaces, especially or interfaces, liquids, glycolipids on their surface tend to form these structures. And the funny thing is, as I will show you later, you see these fine structures in the polymer. What you also see if you do it on the surface, you see fine structures on the bacteria, and that's very difficult. Let's see if it's programmed. No, it's not programmed because this thing has a magnifying glass, I know, but basically what you see here is these fine lines, cilia, as they are called, or flagella, which the bacteria use to move. And if you look very closely here, I hope in the projection one can see it, you see their images here in the polymer, if you resolve fine enough. It's basically a master student sitting in front of the AFM for weeks, but it worked out. So basically we have a means to very finely reproduce the bacterial surface. And this becomes interesting then for further research because it's not only about imaging, it's about thinking about functionalizing tips and getting chemical information into there. So our next step was saying, okay, in molecular imprinting, we can do imaging, we can do nice resolution, we can depict our surfaces. Is it possible to get a first idea of actually independently testing the claim of molecular imprinting that the functionality inside a cavity differs from the other parts of the polymer. And we are also only at the first step, but in a very coarse way, what we did here, is using force distance measurements in AFM. That's not exactly chemistry, that's micromechanics. But if you basically lower the tip on a surface and retract it again, what will happen that at a certain distance it will snap into contact, and then the force increases because you bend the cantilever, and when you go away again, adhesion forces keep the tip on the surface, and at a certain point it snaps off. So you get force distance curves like this, and from those you can measure micromechanical properties. And the interesting thing is that if you look into adhesion mode without too much detail, what we see is that the polymer surface and the bacteria have different adhesion. We are in the micronewton range. And this difference is statistically significant because the precision of the measurement is somewhere in the plus minus 0.05 micronewton, somewhere in that region. The funny thing is that the same is true for the imprint. And that's a little bit surprising and points into the direction, okay, there must be some difference, although we don't understand the chemistry behind it. And it is a little bit surprising because it's polystyrene. But it is reproducible. So what we can say, and I might use this as one of the last, is that in fact, if we look into topography images, adhesion images, phase images, error images, on the one hand, we see these fine structures on the bacteria surfaces. So we see that something's happening there. We can correlate and say where we have topography, where we have bacteria, we have lower adhesion, where we have the polymer, we have higher. The same for the imprints. On the surface, we have a little bit higher adhesion than with the bacteria when we wash it with SDS and in this case, acetic acid. So something is in the cavities that makes the surface different. In this case, most probably parts of the bacteria, which we didn't wash out. That's also something which people didn't know before. Because if we wash it, well, here in the thin film, it's the same, but if we wash it with acetone, adhesion is the same. But it may also be that it destroys the thin film. And that's what I said, we really don't understand the details of the physical chemistry of the films there. And I haven't been talking now about surface charges and zeta values and so on. So it's much more complicated than we ourselves thought. Nonetheless, if we look into the surface roughnesses, if we look into the adhesions, we see that actually we really need to treat our polymers quite harshly. Acetone is quite brutal in this case to get to the same values back again as the clear polymer. So it seems we have the tools for understanding those interfaces much better. And that's something I've shifted from analytical chemistry to the Department of Physical Chemistry. Frankly speaking, for organization reasons, my dean wanted me to manage a transition. The second in my life, seems to be my job. But it made me very interested in things. So, and I think we will need more on the chemometry side here too. So with this, I'm at the point of acknowledging the group. Actually, if you look at the work here, so that's a group photo, the bacteria work on AFM Raman, that's Birgit, a PhD student. The one on the Pickering emulsions, that's Martin here. The fundamental QCM data, what you saw with Ferritin and TMV, that's Christina here. And the human serum albumin work is Visnu, he's from Indonesia. I didn't show you Soat here from Saudi Arabia. She works on a similar topic with insulin, which I haven't shown here. I also acknowledge funding of the group during the last years. We have at the moment Austrian national funding, so that's applied science, that's fundamental science. We had quite some funding from the European Commission in the course of the years. And I thank you very much for your attention. And if you're curious, please fire your questions at me.
Thank you very much, Professor, for your lecture. Now, if there are anyone who wishes to ask the questions in the audience, please, you are welcome.
Thanks for your very nice presentation, nice talk. I want to ask you about the Stern-Vollmer equation. It's on 16 slides. How you confirm that there is a static convention, not a combination of dynamic and static convention, and how you can evaluate the amount of binding energy if it is only static convention.
Okay.
I think so. It is
no,
not.
Sorry, I was on the wrong one here. I need to check in the spectroscopy details there. I have to
Maybe you make some temperature experiment at different temperature.
I suppose that was the one here, but these are at a single temperature.
And
but the binding constants, we don't calculate the absolute binding constants from them. We just say the relative.
Why? If it is static, you may do that.
Basically, if you want to have a frank answer for that, is because we are not fluorescence spectroscopists, but we wanted to go on the mass-sensitive data. So we use the fluorescence for screening purposes.
Okay.
And evaluate the data on mass-sensitive because that's easier for us. Because there we have the direct binding equilibrium on the quartz surface, depending on concentration, and we have the direct mass signal.
Okay.
Makes it easier to calculate here.
Thank you. And a little bit question about temperature. Is it possible to use temperature as a parameter to increase the selectivity because particles which... No, you understand the question, yes?
Well, the point is the particles that I showed you here were eluted at 60 degrees centigrade.
Oh, okay.
So per se, there you get higher selectivity because they have been selected for that. The problem with temperature is that if we go too high, there is a small problem, which is that the QCM is optimized. So the temperature coefficient of the quartz is 0 at room temperature, but it is not 0 outside. And if you change the temperature very strongly, the bigger issue is that you change viscosity and density. And the biggest issue is that, of course, this binding event that you have always works again, or thermal energy works against this. So we get into the good old Arrhenius problem there. So on the QCM, we prefer to keep our temperatures constant.
Okay, thank you.
Thank you for the beautiful talk. I'm not an expert on Stern-Vollmer constants, but I think one useful piece of information you can get if you separate the Stern-Vollmer constant into actually the fluorescence quenching and the lifetimes, because they do look like a little bit like static quenching.
Okay.
But yeah, but that's not my
No, but
sure.
That's good to take on because we didn't look at the lifetime of the signal.
Okay, good.
We have a very simple fluorescence spectrometer, so we didn't take time signals. We just said, okay, that's very close. But there is a point. You have a point there, of course.
Sure,
absolutely.
sure. And it's a minor point. Yeah, but my question is actually about the future. So you showed beautifully, and I really like your elegant way of inverting the measurements, increasing the mass, and growing that imprinted polymer on the surface the way it was. I thought it was very clever. But when you think about imprinting, everybody still mostly looks at sensing. That is my impression. And I think you can do much more. For example, if you imprint transition state analog, you can control rates of chemical reactions, make enzyme analogs. What do you think about that?
There is actually quite a huge body of work. So I showed you sensing because we work on it. That's and many people publish on sensing because it's probably the most low-cost way you can get around those.
Exactly.
And there is nothing bad about it. I mean, there is good science with not too much money also. So that's definitely an important point. I mean, one of the reasons why we want to understand the physical chemistry behind it better is
and I'm probably shooting in my own knee now, but that molecular imprinting has not delivered on the promise it makes for 2 decades now to replace antibodies. And the problem is still within these binding, very high, let's say, distribution of binding affinities, which on the other hand, if you think that radical polymerization or polyadditions are really very statistical processes, and as we know already, or we have the idea that those polymers, when we mix styrene and divinylbenzene, they are not homogeneous, not at all. I mean, where molecularly imprinted polymers are commercially available is in special cases for separation, monolithical columns for HPLC, and for selective enrichment, solid phase extraction. That works quite well.
I think the maybe problems partially is with chemistry used for polymerization. As you said exactly, if it's a radical polymerization, it's a random process. If you introduce elements of dynamic covalent chemistry, which can repair itself, adjust for the imprinted transition state analog or sensing molecule, that could be better.
And there is work also on artificial enzymes based on MIP, but the problem there is that those, or let's say the MIP are not dynamic, they are static. And you know, an enzyme changes conformation. So yes, it works in principle. But what I've seen is work also by Sergei Piletsky, for instance, where they used molecularly imprinted particles to capture signaling molecules that help bacteria to form biomolecules. So this so-called quorum signaling and things like this. But most of it is still research. And at the end of the day, I would like to see something in application. I mean, academia is fine and research is interesting, but at the end of the day, you want to see, does it make a difference, or is it a nice game for half a lifetime?
So, thank you a lot. So, I'm a computational chemist working in organic chemistry, in catalysis, and I deal with molecules, with chemistry on the molecular level. So, for me, chemistry is everything about molecules. And you've shown us quite complex systems. They are nanoscale or even microscale. And I've seen also many materials chemists, nanochemists who show really complex systems. They provide microscopy and something like Raman, for example, which is better. But I would say that they don't provide any information about the systems on the molecular level. And I'm quite curious, and sometimes I even don't, believe in some conclusions, but I believe you. You definitely try to get to the molecular level and to explain everything, but some people don't. And for you, I have a question for someone like responsible for the editorial process, involved in the editorial process. What can be done to increase the reliability of chemical analysis on the molecular level, reliability of structures shown in chemosensors, like in nanochemistry and chemistry of complex systems? Okay. Is there any progress towards that? And what?
Well, that would be a presentation on its own right.
Yeah.
But okay, first of all, I'm not a synthetic organic chemist. But let's say I don't fully agree with you if you say that that's on the molecular. I agree with you that we don't understand many levels on the molecular level, but if you think about nanoscience, it is often about crystalline systems, about solid state chemistry, so where we have a different understanding, of course, of the chemical details, probably added by the complexity that we still don't know how the surfaces exactly look, because that's a topic on its own right. And also with molecularly imprinted polymers, I mean, we try or we venture in understanding what's happened there if we have functional group distribution and so on. But the problem is in molecular imprinting, if you think you have a monomer mixture, you polymerize it. So basically your bulk material has a certain molecular composition. And what we assume is that the distribution of functional groups on the surface, the exact one, differs from inside the cavity to outside the cavity. Now, analyzing that thing on a molecular level is close to impossible with the tools that we have, because we cannot do atomic resolution functional groups on the polymer surface. So the first issue is that we always have aggregate data. And that it seems to work, we see from the fact that we have these binding constants. We can calculate back to, I don't know, this must be something like 2 hydrogen bonds per molecule or something like this, that's possible. But this is actually a discussion persons working in molecular imprinting are having with persons who have a background in organic synthesis, basically since the advent of the field. And I really want to be this understood as a matter of fact statement. So I don't complain and anything, but it is actually, this molecular imprinting part comes more from the material science logic, in the understanding that you cannot have atomic resolution. But I agree with you, if I look into the MIP literature, it is, well, basically it's not big science taking a polymer system and taking every molecule that doesn't jump away from you, squishing it in there and squeezing it into a paper. So it has now become common sense that even if people cannot provide the detailed analytical data here, that we expect them to at least show, so without selectivity I don't accept anything. So if you submit a sensing paper on MIP or a receptor and there is not a reasonable selectivity study in there, then it's desk rejection. That's very simple. Yeah. And if possible, we want people to demonstrate that it works in a real-life matrix, or at least close to it. So if it's not urine because they don't have ethics, it should be artificial urine or something like a matrix. That makes sense. But getting into NMR or something, I know that the standards of organic synthesis would be NMR, and if you want to publish it in or as a new substance, you need high resolution X-ray structures and things like this. I don't think we are there with polymers yet.
Yeah. It's everything about the best practices and about advancing best practices, of course. Yeah. Thank you.
Professor, thank you very much for answering the received questions, but unfortunately we don't have any time to listen to them all. So let us once again thank Professor Peter Lieberte for his lecture.
Thank you.
Ladies and gentlemen, the next 10 minutes are going to be a technical break. We will get in touch with the Symposium Diazo 2021 and our online viewers. We are getting ready for the main part of the closing ceremony. Thank you very much. Ladies and gentlemen, let us once more greet all the guests and online viewers of the Mendeleев conference.
So, this was an incredibly productive week, and we have to admit that we all were inspired by the mutual respect, friendship, and unity throughout all the conference. And that is all thanks to you, the participants.
Since our conference is a large-scale event, which we admire very much, we suggest that it would be interesting and curious to learn about some statistics of Mendeleев 2021, which the organizers were collecting during this week. Let us provide you some numbers and facts, which you can see on the screen as well.
The number of registered participants of the conference is 834, and the invited special guests are 32 people.
528 posters were presented, and the number of oral presentation is 194.
The number of offline participants was 502.
And the number of online participants were 332.
The participants have arrived from many countries. To be accurate, 20 countries. These are Germany, United States of America, Great Britain, Armenia, Belarus, France, Germany, Italy, Japan, Kazakhstan,
Moldova, Pakistan, Poland, Austria, Azerbaijan, Mongolia, Canada, India, Nepal, and Russia.
The conference had 2 satellite events. These are the 6th International Symposium, the Chemistry of Diazo Compound and Relative Systems, Diazo 2021, and RIDL 2021 Conference, Research Infrastructure and Laboratory Design.
There were some special events, such as awarding ceremony, the roundtable, the seminar, and the sponsor presentations, and social events that were in St. Petersburg, Peterhof Palace, and in the research centers of the Institute of Chemistry.
And on this slide, you can see the distribution of the number of participants by the sections. As you can see, the biggest number of participants were at the section of inorganic and organometallic chemistry.
And we are very grateful to the general sponsor of the conference, Gazprom Neft, and to other sponsors, which help was very useful for the conference as well.
Of course, the atmosphere of the conference couldn't be such inspiring without all of you, without our participants. And the photos you can see on the screens.
In conclusion of the presentation, we would like to give a special shout out to all the volunteers of the conference. Please give a big round of applause. Thank you all for your help and participation.
And now we are able to show you some opinions and reports of the participants on the conference.
Hello, dear colleagues. Glad to see you all here in Mendeleев 2021.
It was really great experience here. I really enjoyed every day. I'm really glad I attended the conference. The jury is very friendly and always ask questions that makes you feel seen and involved.
Thank you for organizing me to this opportunity to participate in this conference. It was a nice event.
I consider Mendeleев as a great option to present your research, to show how great impact you did to the science.
We are first time participate here exhibition and very happy to be next time again.
So, as you can see, the final statistics are rather impressive. And thank you for all the participants for your participation and help. Please give a big round of applause.
Let us now talk about our sponsors who play a vital role in our conference through the years. The special guests from Eurochem are present in the hall today. On the territory of Leningrad region, Kingisepp district, the company is represented by LLC PG Phosphorite. The
company's share in the Russian market of phosphate fertilizer is more than 10%. In 2019, on the territory of the industrial zone, Phosphorite was open enterprises of JSC Eurochem Northwest for the production of ammonia, created more than 200 new jobs. So we offer you to watch a short video from the Eurochem. Please attention to the screen.
Компания «Еврохим», один из ведущих мировых производителей минеральных удобрений, реализует крупные инвестиционные проекты на базе Ковдорского, Гремячинского, Усольского горнообогатительных комбинатов и нового месторождения в Саратовской области. В 2021 году в Санкт-Петербурге Еврохим создал собственный уникальный лабораторный центр для проектирования горно-химических предприятий и проведения прикладных научно-исследовательских работ. Центр специализирован на калийных и фосфатных рудах, оснащен самым современным оборудованием от ведущих мировых производителей, соответствует мировым трендам экологичности и технологичности. В составе центра 3 лаборатории. Технологическая лаборатория позволяет проводить исследования по всем технологическим переделам обогащения руды флотационным методом. Реализована возможность выполнения исследований галлургическим способом обогащения. Оборудование аналитической лаборатории определяет до 70 химических элементов, обеспечивает полное сопровождение технологических исследований, работ по гидрозакладке и сопровождение геолого-поисковых работ. Комплектация лаборатории физико-механических свойств горных пород позволяет выполнять исследования методами одноосного и трехосного нагружения. Лаборатория проводит длительные эксперименты по определению реологических свойств солей и закладочных материалов, структурно-текстурный анализ горных пород, разрабатывает технологии ведения закладки в выработанные пространства рудников. Новый лабораторный центр полностью экологичен. Здесь установлены современные системы аспирации для очистки воздуха от химических паров и вредных выбросов. Наличие собственной исследовательской лабораторной базы позволит вовлекать в отработку новые типы руд, уменьшить экологическую нагрузку от горно-химической деятельности и обеспечит безопасность калийных предприятий. Сегодня, в год науки и технологий России и к своему 20-летию, компания «Еврохим» открыла в Санкт-Петербурге уникальный центр научных компетенций на уровне мировых стандартов.
We are pleased to inform you that the partner of Mendeleев 2021 conference, the company Eurochem, announces the international competition for the best proposed solution to a problem for the Eurochem enterprises.
The company has brought out a technological challenge, which we will announce shortly. But first, we have to say that exclusively the Mendeleев 2021 and Diaza 2021 participants can take part in this competition.
So, the task is the following. The flotation is central in the processing of sylvinate ores. Non-stop production process are introduced at the factories. The processing involves ores from various areas of the mine deposits, differing in their material and chemical composition. When enriching various types of ores, the technological personnel of the factories have to adjust the conditions of the flotation process. When enriching ores with high magnesium chloride content, more than 2%, the flotation process is distorted, with a decrease in technological parameters for the following reason. Magnesium ion salts are also floated into the sulfide concentrate, which decreases its quality and, respectively, to the release of defective products. A significant fraction of the collector aliphatic amines is sorbed on the surface of magnesium ion salts, which entails overspending of the collecting mixture. Magnesium ion salts accumulate in the circulating matrix liquid, which ultimately leads to a complete disruption of the solvent flotation process. The content of magnesium ion salts in the circulating solution should be at the level of 0.2 to 0.5%. The priority task is to seek a method for the preliminary separation of magnesium ion salts from the circulating solutions. A related task is a search for the method for the subsequent processing of magnesium salts into a commercial product.
And briefly, the points you have to cover. Firstly, to carry out a literary and patient review on the available technologies for the isolation and processing of magnesium ion salts. Secondly, suggest methods for the isolation of magnesium ion salts and their purification for commercial purposes. And thirdly, they propose an optimal method for the preliminary isolation of magnesium salts and the issue recommendations for the use of magnesium ion salts in commercial products.
The author of the best solution, which will be chosen according to the opinion of Eurochem jury, will receive a laptop as a prize. You can see it on the table. Your decision can be sent to the address reported on the slide by November the 30th, 2021. On 25th of January, by the decision of the expert committee, the best solution will be chosen. The winner will receive the prize.
We wish good luck to those who will take part in the competition, and we are thankful to Eurochem for the attention to our conference and for organizing such a creative scientific competition for
anniversary of Eurochem, and we congratulate the company on that. At the same time, the year 2021 is declared as the year of science and technologies in Russia. In such a special year, the Eurochem company officially announces the opening of the Laboratory Researching Center in St. Petersburg as a company's project.
We have received a letter from the Vice Governor of St. Petersburg, Vladimir Nikolaevich Knyginin, on this occasion. You can see it on the screens. In brief, it says that Vladimir Nikolaevich Knyginin is happy to greet everyone on the opening of the Eurochem Laboratory Research Center. He acknowledges modern equipment of the center and believes that the center has great scientific opportunities. It is a pleasure for him to say that Eurochem is actively collaborating with the Institute of Chemistry of St. Petersburg State University in this large project. He hopes that this collaboration will help to develop chemical industry in Russia and bring up a new generation of qualified chemists. We thank Vladimir Nikolaevich Knyginin for this message.
We are glad to welcome on stage the representative of Eurochem, who will tell us more about the project. Sergei Sergeyevich Galibeev, the supervisor of research and technological development of the United Institute Eurochem SWEC.
Good afternoon, dear colleagues. First of all, I would like to congratulate you with the successful end of the conference. A lot of members, it's great. And the second one, I would like to congratulate our company Eurochem, with very important event, because today we are opening our first research facility in this field, in the field of potash and phosphorus mining and processing. Why is very important for us? Because Eurochem is the first company in modern Russia that developed and established whole cycle from mining to commercial production of potassium chloride, and it's very important. Our first project was in Perm region. After that, we established the second project in Volgograd region, and now we are starting our activity in third project in Saratov. To be competitive in this potash business, very strong R&D activities and competences very important. Why so? Because each deposit is very unique. A lot of different things like geophysics or for example, composites and so on. And it's very important to have very strong competences and good R&D facilities. And I suppose this new R&D center in Eurochem project is very important, but only first step to develop our potash business, because only yesterday our board of directors of our company decided to create Unified Design Institute, and one of the activities and in this United Integrated Design Institute, we are starting the new activities, R&D activities, for example, in nitrogen fertilizers, to create the new type of nitrogen fertilizers or modified the product portfolio of our company. And we believe that to be the success in this activity, very strong relationships with scientific community, and especially with Institute of Chemistry of St. Petersburg is very important. And I hope that we will have a lot of joint scientific projects in the nearest time. Thank you.
Thank you very much for your speech.
St. Petersburg State University became the first research and educational center to conclude a cooperation agreement with Eurochem for the implementation of future research projects in conjunction with the new Eurochem laboratory in St. Petersburg. Now it is honor for us to welcome on the stage the head of research of Eurochem project, Vladimir Vasilievich Savchenko, and the Deputy Vice Rector for Scientific Work of the St. Petersburg State University, Anastasia Sergeyevna Yarmash, for signing a cooperation agreement. Thank you very much.
Thank you very much for invitation, for the productive conference, for being here. I would like to stress that as a mineral and chemical company, Eurochem is very interested in developing cooperation with the international chemical community as a whole and Institute of Chemistry, St. Petersburg State University in particular. We believe that our cooperation, multi-purpose cooperation, mutual beneficial cooperation will become stronger and deeper every next year. And we in our company are ready to do our best for that. Thanks.
Thank you.
So, for the presentation of commemorative chemical utensils from the laboratory of Dmitry Mendeleev as a symbol of continuation of the Russian chemical school traditions in Eurochem system, we welcome on the director of the Institute of Chemistry, Professor Irina Balova.
And the deputy head of the Division of Large Projects Management, Alexey Sergeyevich Vertягин.
First of all, I'd like to thank Eurochem for the support of our conference and our event, and in honor of your anniversary, 20th anniversary of Eurochem and our start of our cooperation, I hope for the long time in the research and education both. I give you this present, a piece of the glass from the 19th century, from the laboratorium of Dmitry Mendeliev, as a symbol of our cooperation in the future.
Я, позвольте, по-русски. Сегодня действительно знаменательное событие. Мы подписали с древнейшим российским университетом соглашение о сотрудничестве. И это знаменательно, что сегодня год 20-летия Еврохима. И вопрос науки, который действительно остро стоит и ставится президентом, очень важен. Мы действительно инвестируем время, деньги в развитие научной базы. И это позволит нам добиться успехов в устойчивом развитии, в создании современных, экологически чистых, безопасных производств. Спасибо. Очень горды.
May I add some words in Russian? Sorry for our foreign participants, but я бы хотела сказать, что для Санкт-Петербургского университета, в частности, для Института химии, вот это событие в закрытии нашей конференции является очень знаковым, поскольку мы впервые начинаем такое сотрудничество с компанией, работающей в реальном бизнесе. И мы бы хотели, чтобы наши научные исследования, то, чему мы учим наших студентов, аспирантов, приносило пользу, и не только результатом этих исследований являлись научные статьи, а те продукты, которые мы сможем, я надеюсь, наукоемкие производить вместе. То задание, которое сегодня получили наши участники, вот это может быть первый такой небольшой пилотный проект, который, я надеюсь, разовьется в более крупные проекты, которые будут иметь успешный результат и полезный для всех нашего общества. Это точно. Спасибо еще раз.
Irina Anatolievna and Alexey Sergeyevich said that both the sides appreciate this moment and they are very glad and happy about the signing these documents and for the collaboration of both the sides.
So, and now it is the moment we all have been waiting for.
The most long-awaited moment of the closing ceremony, the naming of the best reports.
And we are glad to welcome on stage the Scientific Secretary of the conference, Vladimir Mikhailov, for the award ceremony.
Thank you. The best poster presentation in section Analytic Chemistry is awarded Kochetkova Maria from St. Petersburg. In section Computer Modeling and Chem Informatics is awarded Krivoshapov Nikolai from Moscow. In section Inorganic and Organometallic Chemistry is awarded Solomatina Anastasia, St. Petersburg, from St. Petersburg. In section Nanochemistry and Nanomaterials is awarded Orujev Farid from Makhachkala. In section Organic and Biomedical Chemistry is awarded Lebedev Andrei from St. Petersburg. In section Polymer Science is awarded Krivovisheva Vasilisa from St. Petersburg. Diploma for the best presentation in DIASA 2021 is awarded to Ksenia Barashkova from Moscow. Идет, да? The best flash oral presentation in section Analytical Chemistry is awarded Faleva Anna from Arkhangelsk. In section Computer Modeling and Chemoinformatics is awarded Alkhimova Larisa from Tyumen. In section Inorganic and Organometallic Chemistry is awarded Zavyalova Anastasia from St. Petersburg. In section Organic and Biomedical Chemistry is awarded Tsuda Masato from Tokyo, Japan. The best oral third-degree presentation at section Analytic Chemistry is awarded Tagirova Madina from Moscow. In section Computer Modeling and Chemoinformatics is awarded Rehimbekova Asima from Kazan. In section Inorganic and Organometallic Chemistry is awarded Dayanova Irina from Kazan. In section Nanochemistry and Nanomaterials is awarded Reichstein Jakob from Erlanger. In section Organic and Biomedical Chemistry is awarded Vidyakina Alexandra from St. Petersburg. In section Polymer Science is awarded Kashina Anna from St. Petersburg. The best oral second. The best oral second-degree presentation and section Analytic Chemistry is awarded Zarachintsev Alexander from Moscow. Зароченцев Александр. In section Computer Modeling and Cheminformatics is awarded Vlasova Yulia from Moscow. In section Inorganic and Organometallic Chemistry is awarded Gurina Galina from Nizhny Novgorod. In section Nanochemistry and Nanomaterials is awarded Bajo Ignacio from Erlangen. In section Organic and Biomedical Chemistry is awarded Petropavlovskih Dmitry from Moscow. In section Polymer Science is awarded Karpov Valery from Moscow. In Diaza 2021 is awarded to Katarzina Orlovska from Poland. The best oral first degree presentation in section Analytical Chemistry is awarded Kovalenko Alexander from St. Petersburg. In section Computer Modeling and Cheminformatics is awarded Alexandrov Evgeny from Samara. In section Inorganic and Organometallic Chemistry is awarded Grudova Maria from Moscow. In section Nanochemistry and Nanomaterials is awarded Guselnikova Olga from Tomsk. In section Organic and Biomedical Chemistry is awarded Vil Vera from Moscow. In section Polymer Science is awarded Akhmetov Nikita from Moscow. In Diaza 2021 is awarded to Ilya Filipov from St. Petersburg. And special prize from Nanomaterials Journal is given to Sviridova Елизавета. The Mendelеев 2021 conference is closed. See you. Repeat. The Mendelеев 2021 conference is closed. See you in 2023. Thank you.